Welcome, and thank you for joining us for today's webinar, Pump Two-Phase Cooling, the Solution for High Heat Dissipation and More, presented by Advanced Cooling Technologies and TechBriefs Media. I'm Bruce Bennett, editor at TechBriefs Media, and I'll be your moderator today. This webinar will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by using the Ask a Question box on your screen. Our speakers will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered offline. To view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce today's speaker. Devin Pellicone is the lead engineer of industrial projects at Advanced Cooling Technologies, Incorporated. He has over 8 years of experience developing advanced thermal solutions for a wide range of aerospace, military, and commercial applications. He has a Master's of Science in Mechanical Engineering from Villanova University with a concentration in thermal fluid systems. Mr. Pellicone has extensive experience developing both active and passive solutions for challenging electronics cooling applications, with a particular expertise in evaporative solutions. He has successfully demonstrated prototype thermal management systems for directed energy weapons, power flow, controllers, laser diodes, and a variety of high heat flux electronic applications. He has been awarded numerous research grants to develop pump two-phase flow solutions and has published several papers on the topic. Now that you're familiar with our speaker's qualifications, let's begin today's presentation.
Thanks, Bruce. I'm Devin Pellicone, and we'll be talking today about pump two-phase cooling and how you can utilize it in some of your systems. Throughout today's presentation, we'll talk about some current trends in thermal management technology and what's leading towards the need for pump two-phase cooling. We'll explain what pump two-phase cooling is from the basics, and we'll give you some examples of our both custom and off-the-shelf solutions. We'll end with some case studies relating to pump two-phase applications, and we'll finish with your questions. Current trends in power electronics and other electronic applications are requiring more and more power from the devices. Increasingly, the device sizes are also decreasing, leading to higher heat flux situations. Traditional cooling methods like air cooling and liquid cooling are approaching their usable limits in applications like high-powered IGBTs, hybrid electric vehicles, data centers, and even laser diode applications. Pump two-phase can solve a lot of these challenges while providing a high-efficiency, more energy-efficient solution for the increasing demands of most applications. Some key markets that can benefit from pump two-phase cooling technology are power electronics like IGBTs and other semiconductor-based components. Some data center applications where they have particularly high-performance computing and high-powered chips, and also laser diode arrays for types of applications where high-powered lasers are being used for industrial processes or other applications. Trends in the market, specifically in data center applications, include increased cooling medium temperatures, the need to operate the data centers at higher temperatures for better energy efficiency, smaller packages in all of the key markets, including data centers and power electronics, trying to get more power per unit area, and obviously trying to drive the components harder with higher power outputs. All of these things result in larger thermal problems that need to be resolved. Some of the common thermal design pitfalls include inefficiency or insufficient cooling solutions. A lot of times the cooling solution is an afterthought to the design process, which results in an undersized cooling approach. A lot of applications that have high power today default to a pumped liquid cooling solution, which can often result in large pumping powers, high flow rates, and lots of challenges that we'll discuss later in the presentation. Pump two-phase cooling is, as the name suggests, a two-phase cooling approach. It utilizes a working fluid that boils as it picks up heat from the heated components. We utilize the latent heat of vaporization to absorb much more energy than you could with the sensible heating of a liquid. Typically, this results in 2 to 4 times the amount of heat transport capability as compared to sensible cooling approaches like water glycol systems. The difference between a glycol system and a pump two-phase system is that the water enters the system at a saturated condition, meaning it's close to its boiling point. As it flows through the heated component, it picks up that energy and boils the fluid, transitioning the liquid to its vapor state. The vapor then travels on to another part of the system where it is condensed, gives off its latent heat, and the cycle repeats. Comparing pump two-phase to single-phase solutions, if you were to look at the systems from the outside, they'd look nearly identical. They both include a heat exchanger, a reservoir, a pump, and a cold plate. The difference between a pump two-phase system and a single-phase system mostly relies on the size of the pump. Because you're utilizing the latent heat of the working fluid, you can get away with significantly less pumping power. We'll provide some examples of exact numbers for that later on. Here's a quick video to demonstrate the differences between pump single-phase and pump two-phase.
Pumped two-phase, or evaporative cooling systems, use the same basic system-level components as the pump single-phase system. However, pumped two-phase systems typically use refrigerants as the working fluid. Through refrigerant selection and appropriate controls, the refrigerant is designed to boil as it acquires heat from the hot surface of the device. More heat can be removed through the boiling process, otherwise known as latent heat, than through sensible heat with single-phase cooling. Boiling across the entire evaporator surface offers a further advantage in that the evaporator will have a very uniform surface temperature, typically within a few degrees.
In this video, we want to show the boiling process as it moves across a heated cold plate. What you'll see is the fluid entering the cold plate from one end, boiling and generating bubbles as it moves from one end of the cold plate to the other. Let's watch.
In this video, a thermal load is applied across the plate. As the fluid travels, it begins to boil. The boiling process removes the thermal energy from the component and carries it to the end of the plate. At the exit point, the working fluid is 50% liquid and 50% vapor.
As you can see, the boiling process can be very effective. Now let's compare two-phase systems to single-phase system using some numbers. Let's assume an 80 kilowatt total power system. If you were to use a single-phase system using a typical cooling oil in the military industry, PAO, you would require 134 liters per minute, or 35.4 gallons per minute of flow rate, to achieve a temperature gradient across the plate of about 20 degrees C. That results in a pumping power of about 5.3 kilowatts. If you were to dissipate that same amount of power with a two-phase refrigerant loop, in this case assuming R245FA, you'd need about 25 liters per minute, or 6.6 gallons per minute of flow rate to achieve the same performance. That's an 80% reduction in pumping power. So you only need 250 watts to drive the pump in this system. That's significant. As alluded to earlier, some applications that benefit from pump two-phase cooling mostly rely around high heat flux applications. Laser diode cooling is a good example because you often have very high heat loads in very small packages. These heat fluxes can be greater than 500 watts per centimeter squared, and they typically require quite cool temperatures, needing low thermal resistance. Can also cool parallel components with a pump two-phase system by incorporating flow restrictions at the entrance to multiple cold plates. All of the cold plates can be then operated at the same temperature, improving the isothermality across the system. Power electronic applications benefit greatly from pump two-phase systems because they typically require dielectric cooling. If there ever were a case where the refrigerant would egress from the system, it has electrical isolation and wouldn't short out any high voltage components. This provides some additional safety benefits to a lot of power electronics designers. Some additional capabilities for a pump two-phase system include the ability to transfer heat over long distances. You can pump the refrigerant through a cold plate, and then many feet of tubing later, you can dissipate that energy to a condenser. That allows remote cooling for components in tight packages. We mentioned you can accommodate multiple cold plates in parallel, which is of benefit to a number of different systems, and it can operate in any orientation, which is valuable for aircraft applications or any application where your hot components may be articulating. It's also possible to dissipate heats over large areas with pump two-phase cooling. At Advanced Cooling Technology, we've demonstrated cold plates upwards of 1.8 square feet in area. Now we'll send it back to Bruce for a quick polling question.
Our first polling question of the day: what is your principal interest in pumped two-phase cooling? A, more academic, I want to learn about new thermal technologies. Or B, more appreciation related, I think my company's products may benefit from this technology.
Thanks, Bruce. Here's a video demonstrating pump two-phase cooling with multiple evaporators. In this test setup, flow is entering the cold plates from the bottom. And what we're showing on the video are 4 independent cold plates with their heat loads turning on and off. All of the cold plates are serviced by the same pump and the same manifold on both the upstream and the downstream portions of the system. As you watch the video, you'll see dots turning on and off, which is indicating the power being turned on and off to that particular evaporator. You'll watch the bubbles disappear in the evaporator as the power goes away. What you can see is that flow is not disrupted to the other components that still have their power. This is a big benefit of pump two-phase cooling if designed properly. Let's watch the video. High heat flux components don't necessarily need to be cooled with a two-phase cooling approach. It can be done with single-phase cooling. However, the challenge is that a large amount of flow rate is required. This often means spending high velocity fluid through the cooling channels as opposed to a two-phase system, which would be a much lower flow rate. If you do try to send single-phase fluid at a high velocity through coolant channels, you run the risk of eroding the channel walls. This is particularly of issue in microchannel coolers for laser diode applications, where the very small hydraulic diameter of the channels results in very high velocities. As the single-phase fluid flows through the channel at high speed, it tears away at the walls of the channel, as you can see in the image on the right. Over time, the channel walls can deteriorate to the point where they no longer contain the fluid, which results in a failure. Pump two-phase systems with their much lower flow rate do not have this issue. Some additional benefits of pump two-phase cooling, apart from the lower pumping power and lower flow rates that we've already discussed, you can achieve higher degrees of isothermality across your components. Since the boiling process occurs across a constant temperature, all of the components seeing the saturated fluid will operate at close to the same temperature. For instance, if you had 5 chips all in the same coolant channel, the first chip and the last chip would see the same coolant temperature. That's not the case in a single-phase system, as the fluid picks up temperature as it flows across the heated components. The higher heat flux capability of pump two-phase we've addressed is also an issue when trying to achieve this with single-phase cooling. And also the higher efficiency of a pump two-phase system allows for higher ambient temperatures or higher cooling medium temperatures. This is a particular benefit for data center cooling applications where you want to reduce the load on your chiller and improve your energy efficiency. Also, the dielectric nature of most two-phase fluids is a major benefit for high voltage applications and applications where electrical isolation is important. Now we'll hand it back to Bruce for a final polling question.
Thank you, Devin. Our second polling question of today is, which of the stated benefits of pumped two-phase cooling benefits would be most important to your company's products? A, higher heat dissipation capability. B, reduced space claim for thermal management. C, more isothermal device temperatures. D, lower power requirements. Or E, increased protection for leaks.
Thanks, Bruce. Now that we've discussed the benefits of pump two-phase system, let's discuss some engineering considerations. First question that often comes up relating to two-phase systems is related to flow instabilities. Flow instabilities can occur in a pump two-phase system that's poorly designed if the system is allowed to violently boil and push fluid back out the inlet of the channels. This occurs when the fluid reaches a superheated condition before it exits the cold plate and violently boils, forcing liquid back out the inlet. In a properly designed two-phase cold plate, the system always finds an appropriate place to boil, and the fluid is always moving in the proper direction. ACT has years of experience developing evaporators for two-phase systems to avoid this situation. Flow instabilities can also occur in parallel channels or parallel evaporators. As you saw in the video earlier, ACT has developed mitigation techniques for ensuring that all of the evaporators and all of the channels receive the same amount of flow under all conditions. Another concern with two-phase systems revolves around the modeling of the heat transfer and pressure drop in the system to get an accurate prediction of the performance. Two-phase heat transfer coefficient correlations and pressure drop correlations are notoriously inaccurate. Over the years, ACT has developed numerous modeling techniques to provide higher fidelity modeling approaches for a wide range of different applications. One application that we've spoken about is related to high heat flux cooling of laser diode applications. One such application would be laser cutting materials, where the high-powered lasers must maintain a constant temperature over the course of their operation to maintain the proper wavelength of the laser for operation. These laser diodes can have heat fluxes greater than 500 watts per centimeter squared, and often require uniformity across the various components of better than 2 degrees C. If a single-phase cooling system were to try and achieve this kind of performance, you'd require significantly high fluid flow rates, and you risk damaging your cold plates. ACT has developed two-phase cold plates for this application. Shown here is a plot of a cold plate that incorporates 1.8 square feet of laser diode arrays with a requirement to maintain the diodes within plus or minus 3 degrees C across the entire array. ACT developed the cold plate and the supporting two-phase system to be able to achieve these targets as shown on the plot. Also of note here is the accuracy of ACT's modeling approach as compared to the actual experimental data. You can see that good agreement was achieved. On top of custom applications and designs, ACT also has some standard products. ACT recently acquired Parker's Precision Cooling business and extends its offerings of pump two-phase solutions. With this acquisition comes a series of standard pump two-phase cooling products that have been deployed in military and commercial applications. These products have demonstrated thousands of hours of rugged, reliable operation. They use refrigerants, which are both non-corrosive and non-conductive. The product offerings include options for 8 kilowatts, 30 kilowatts, and 50 kilowatts, as you can see in the image on the right. Inside of each of these components includes a pump, a filter, multiple cold plates, a condenser, and an accumulator. The filter dryer is used to eliminate any unwanted moisture in the system, as well as filter out any components that may have been generated. The system includes dry break quick disconnects so that it can be easily swapped, the cold plates from the system if a diode ever needs to be replaced. Now let's talk about a case study for a high-performance computing application. In this case, the customer was Intel, and they were looking for a partner in developing next-generation coolant distribution unit and cold plates for a high-performance computing application. The requirement was for a 4-kilowatt system, and the system had over 50,000 individual nodes, each with a one U-blade configuration. The system had a maximum weight of 12 pounds. The major challenges were the increased heat dissipation requirements within a tight package. ACT utilized a wide array of thermal simulation tools to design and prototype the cold plate you see on the screen. Each of the cold plates are made out of copper, and they're plumbed in series so that every cold plate sees the same flow of fluid. ACT's solution provided even more space savings than Intel originally anticipated, freeing up even more area for the customer's application. Next, we'd like to show a comparison of how pump two-phase cooling compares to more traditional cooling methods for a power electronics application. In this case, we have an IGBT module that needs to maintain a temperature below 120 degrees C. As you can see in the chart, 4 cases were examined: a conventional air-cooled heatsink, a traditional copper tube aluminum plate liquid cold plate, an extended surface liquid cold plate, and a custom-designed pump two-phase cold plate. The IGBT was driven at 1700 volts and 450 amps, and the power was measured until a junction temperature of 120 degrees C was achieved under steady-state conditions. There was also a 220% overload case for a 10-second period. As you can see, the air cooling solution was able to achieve the lowest module losses for the given amount of amperage. In a pump two-phase system, more than double the amount of power was able to be driven through the IGBT module before the 120 degree C junction temperature was achieved. Further comparing the cooling technologies, you can see a list of different metrics for the air cooling, liquid cooling, heat pipe solution, and a pump two-phase cooling solution. As you can see, the pump two-phase system provides the lowest thermal resistance while maintaining the tightest compactness of any solution available. Its cost is somewhere in the middle between all of the solutions, and it provides a high energy efficiency solution for any application. To summarize, pump two-phase cooling offers the potential to address increasing heat dissipation requirements up to 1,000 watts per centimeter squared by some estimates, in which air and pumped liquid cooling just cannot compete. Pump two-phase systems require only a small pump and can be designed to be compact and lightweight. We have reviewed some applications where pump two-phase systems are being implemented today, including laser diode applications, high-performance computing applications, and power electronics applications. As the number of applications requiring high heat flux dissipation capability increase, we believe pump two-phase solutions are likely to become the most attractive solution. Before we take some of your questions, I'd like to highlight a few resources that can be found on ACT's website. This includes more information about our custom and standard pump two-phase products, a pump two-phase product frequently asked question page, and some additional case studies, webinars, and white papers for your review. The slide deck that we presented here today can be available for your review if you send an email to ACT requesting them. We appreciate your time, and now we'll turn it back to Bruce for some more questions.
Thank you, Devin, for that most informative presentation. And if you're ready, we'll get right to the questions from our audience. First question, why is a pump two-phase system more energy efficient than a traditional liquid cooling system?
As we mentioned during the presentation, liquid cooling systems often require faster flow rates in order to achieve the same performance as a pump two-phase system. Higher flow rates and higher pressure drops translate to more power required to drive the fluid around the loop. In a pump two-phase system, the energy capacity and the latent heat of vaporization of the fluid is 2 to 4 times greater than the sensible energy that can be absorbed in the single-phase cooling system, and therefore it requires less mass flow rate to dissipate the same amount of power. Less mass flow rate, lower pressure drops equals less pumping power, which means less energy needs to be supplied to the system for a pump two-phase system as compared to a single-phase system.
Thank you, Devin. Next question. Is it possible to actively control my component temperature with a pumped two-phase system?
That's a good question. In fact, it is. The saturation temperature in a pump two-phase system can be controlled by the temperature at which you condense the fluid. For instance, if you have a condenser that's liquid cooled, if you set the condenser temperature to your desired component temperature, the fluid inside of the loop of a pump two-phase system will operate at that temperature. If you adjust the temperature of the condenser, you can adjust the saturation temperature of the loop, which will adjust the temperature of your component. So it's relatively straightforward to adjust the operating temperature of a pump two-phase system just by changing the temperature at which you condense the fluid.
Thank you. Next question. Are pumped two-phase cooling systems typically pressurized? And if yes, what are the typical values?
They are. They often use refrigerants like R134A or R245FA, and those refrigerants are not liquid at ambient pressures. So the system does need to be pressurized. Typical pressurization ranges from 50 to about 250 psi, depending on the operating temperature of the particular component. There's an entire library of working fluids that we use here at ACT, and we weigh the benefits of using a higher pressure fluid versus a lower pressure fluid and what kind of system level thermal performance we can achieve.
Thank you. All right. One of our attendees wants to know, can you comment further on typical operating costs and footprint differential between pumped liquid and pumped two-phase cooling solutions for the same application?
Sure. I'll start with the footprint differential. As we mentioned a few times, the pump size for a pumped two-phase system can be considerably smaller than the pump size for a single-phase system. That's where the major difference in size of the systems is had. Depending on what the condenser looks like, whether it's air-cooled or liquid-cooled, those components tend to be pretty similar in size between the two systems. So often we find about a 15 to 20% reduction in size with a pumped two-phase system compared to a single-phase system. As far as pricing for those two systems or operating costs go, a pumped two-phase system, like we mentioned, can have 80 to 90% lower energy consumption than a resulting single-phase system. So if you have high electrical costs in your area, then you could see an 80 to 90% reduction in the operating costs from an electrical standpoint. The maintenance between a pumped two-phase system and a single-phase system are virtually identical.
Thank you. What kinds of working fluids are used in a pumped two-phase cooling solution?
Most commonly, we use dielectric refrigerants. They offer good benefits in terms of their latent heat, and they typically have the right boiling point and pressures for most systems. They also don't freeze under normal transit conditions, and they're dielectric, which is a benefit to a lot of applications. But they aren't the only solutions. We've done some water two-phase cooling solutions, as well as some alcohols. So it really depends on the particular application as to which working fluid we use.
Thank you. Is having an accumulator necessary in P2P systems?
It is. The accumulator in a pumped two-phase system serves a very valuable purpose. Because we have transition from liquid to vapor, and vapor is often several orders of magnitude less dense than liquid is, we need a place for that volume expansion to occur. And that's what the accumulator does in a two-phase system. As we transition from liquid to vapor, we're decreasing the density, effective density of our system, which means we need more volume. So if we didn't have a place for that less dense vapor-liquid mixture to go, the system pressure would start to climb, and it would potentially risk safety in the system. So accumulator is absolutely necessary in a pumped two-phase system.
Thank you. How does gravity affect the boiling process?
It's an interesting question. Gravity plays an important role in two-phase systems at both the evaporator and the condenser portion. We all know, as watching a pot boil on our stove, that the vapor naturally wants to rise to the top from buoyancy forces. It's the bubbles you see rising to the top of your pot on the stove. So same thing happens in a pumped two-phase system. The vapor naturally wants to go up, and liquid naturally wants to go down. So we often try to design pumped two-phase systems to benefit from gravity in any way that we can. We have the condensers positioned physically above the evaporators if at all possible, and we have the inlets and outlets positioned such that gravity is always providing a benefit. That's not an absolute requirement of a pumped two-phase system. They can work against gravity if needed. Just needs to be designed around that.
Thank you, Devin. Well, I'm afraid that's all the time we have today. I'd like to thank Mr. Pellicone for giving us such an enlightening presentation, and I'd like to thank today's attendees for participating. That concludes today's webinar, sponsored by ACT and TechBriefs Media.